To set up the work of properly doing error checking, I actually spent a lot of time thinking about the specifications and encoding many of the errors I'm going to check for within this list. Another way to say that is, one of the most intense processes of writing good function files is thinking deeply about exactly what we want our functions to do. In this case, since we're starting anew, I'm going to go ahead and just delete everything that's not an input check, since I'm going to redo that anyways. And then the same thing down here for verifying outputs. I'm actually just going to delete all of this because it's from the dscale function and I want to start fresh. But I do use the structure since we've already kind of figured out what that works. So specifically, the first thing that we're going to do is we're going to check for too few inputs. Here we go. Let's check that the user passes at least 5 inputs into the function. Remember that the way that this function works is that we have 6 inputs: trans, alpha, a, x, beta, y. If beta is 0, we don't actually have to specify y, which means we could get away with 5 inputs. If beta is non-zero, we need y to be given as an input to the function, which means that when we're checking for this error, we want to have at least 5 inputs. Anytime we're writing a function and working to error check and debug, it's important to have a well-studied example that we can use to test our algorithm. We've actually seen multiple videos with the same example referenced each time. In this case, I'm going to use that work to drive the algorithm development. Specifically, we've seen this matrix A where it had 4 rows and 3 columns. And then we had a vector X, which was 3 rows and 1 columns. In the case that we're going to multiply A times X, we're not going to use a transpose. Go back and watch those example videos if you haven't done so already. We're also going to multiply the output by 1 to generate that. Of course, we should specify an input beta, but we're specifically checking that we are making sure that the user passes enough input. So we're going to leave that out and see if we can produce an error message that reminds the user that we need at least 5 inputs. With that, let's go ahead and transition over to our function. Here we have different checks that we've done previously. I'm ready to actually just delete all of this. I think I can get this off of the top of my head. The first thing we're going to do is check that the user passes at least 5 inputs. So here we're going to use an if condition. And specifically, we're going to say if the number of arguments input to the function is less than 5, then we're going to produce an error. Specifically, we're going to tell our users, error, you must have at least 5 inputs to this function. Let's go back to our test driver and we'll actually run this code and see what happens. So here we go. MATLAB's going to test and let's check it out. Okay. We passed in 1, 2, 3, 4 inputs. We see, this condition held. Remember, if you're ever wondering about a piece of code, use the documentation. One of the reasons that I was so adamant in the early part of this class about learning how to read and getting used to reading documentation is so you can teach yourself MATLAB. Syntax is the least interesting part of coding. It is important, but it's one of those things that each of us has to take responsibility for. In this case, nargmin counts the number of inputs. Just go ahead and help that if you need it. Since the number of inputs is 4 and that's less than 5, this holds to be true. We print out this error message, which is exactly what we see. This error code seems to be working well. We could also delete some of these and then test again. Let's run one more time. Yep, it's happening. So we undo. Looks like that error check is going well, which means we can comment that code knowing that we've now checked for at least 5 inputs. Next thing we're going to do, we go down our specification list. We're going to check that the input transpose is either equal to capital N or capital T. If it's not one of those two values, then we're going to produce an error. In other words, we're going to do an error check on the first input, and we want to know that the first input is either equal to capital N or capital T. Let's go ahead and just reuse the previous data that we had. Here we'll go ahead and copy and paste, and then we'll uncomment this. And notice that in this case, let's break the rules. Specifically, we'll set transpose to be the capital letter C, and we'll say this is an error, the first input is not valid. Of course, since we're not testing the number of inputs, we should probably set beta to be 0, and then actually explicitly pass that variable into our function. That gets us ready to actually run the error check for the first input value. Let's go over to our function and create an error check to make sure that the first input takes the proper form. Again, we'll use an if statement to accomplish that. So specifically, we know that the transpose has to be equal to N or T, capital N or capital T, which means if it's not true, we want to produce an error message. Well, not or is not the first one, and not the second one. So in this situation, we say if transpose is not equal to capital N and transpose is not equal to capital T. Here we've got our short-circuited and or short-circuited logical operation. You can see a previous video on that. So if it's the case that the first input is not capital N and it's not capital T, we're going to remind the user that the first input must be equal to a character capital N or capital T, and that's actually case sensitive. So let's save that and we'll go back to our driver. Here we've actually violated that rule. Let's test to make sure that our error condition is working. Yep, when we do this, we see that the first input must be a character equal to capital N or capital T, and it's case sensitive. Let's go ahead and check the lowercase version of this. Same thing, problem. Lowercase version of T, same thing. Now let's go ahead and do N and run. Well, of course, MATLAB is upset because I haven't actually specified why, but we noticed that the error check that we had wanted to check is actually working properly. Let's comment this out since we know that that is now working, and we'll go on to the next error. If we go back to our specification list, we want to make sure that alpha and beta are scalar values that are stored in double precision, so they should be non-empty specifically, and they should also be doubles. We'll go ahead and create a check for that. So we're going to check that scalars alpha and beta are as defined, and specifically we're going to make sure that our function catches it if there's any errors in either of those. So we're going to check that alpha and beta are non-empty scalars stored in double precision. In this case, we already have working input data, so we'll go ahead and copy and paste here, which means we can reuse that work. That's a very, very good thing to do when coding. Here, we're not trying to catch errors in transpose. We are trying to catch errors in alpha. So let's go ahead and set alpha to be empty. So in particular, we're going to say that alpha must be a non-empty scalar. Here it's empty, and we'll try to catch that. We're not ready to do anything with beta, but I will actually store beta as a double explicitly in this situation. Later, we'll go ahead and switch this to single to make sure that we've caught all the different cases. Now that we've set up the test, let's go over to our function file. And in this case, let's go ahead and set up an error that checks that inputs alpha and beta are non-empty scalars. And we're going to do this using the isScalar function. Remember, we saw that in a previous video, and that actually helps us check that these are non-empty. IsScalar guarantees that the value that we're testing is a 1-by-1 if it returns as true, otherwise it returns as false. For this error check, we'll use an if, else, if, and then we'll end. So there's no else condition in this case. And the first condition we're going to check is that the alpha and beta are scalars. Because we want both to be scalars, we want alpha to be a scalar and beta to be a scalar. If that's not true, that means either alpha is not a scalar or beta is not a scalar. So specifically, we'll write if alpha is not a scalar, we'll go ahead and write that, alpha, or if beta is not a scalar, so is scalar beta, if either of those conditions evaluates as true, we'll produce an error message that says inputs alpha and beta must be stored as non-empty scalars, and that kind of triggers for the user. So that first if statement checks for scalars. The else if statement, let's go ahead and check that both of them are doubles. So we want alpha to be a double and beta to be another double. In other words, if that is not true, then either alpha is not a double, so we'll say if alpha is not a double, or is a beta double. So we're testing are alpha and beta are double. So remember, the is a function, we've done a video on this, tests alpha to make sure that it's a double. That produces true if alpha is indeed a double, but then we hit it with a not operator, which means this condition is true if and only if alpha is not a double. If that's true, we drop into the body of the else if statement. That is also true for if beta is not a double, and because this is an or, this, whatever code we put here will run in either situation, if this evaluates as true or this evaluates as true. In either case, we're going to produce the error message that the inputs should be stored as double precision floating point numbers. Let's go back here. The first test that we're going to do is that alpha must be a non-empty scalar. Let's go ahead and run that. Oh, check it out. This is a 0-by-1 or 0-by-0 array. When we drop into this particular condition, alpha is not a scalar, so this becomes true. The moment that the first value in the logical short-circuited OR evaluates, then we drop into this error condition and we produce the exact string that we wanted. We could also test the other situation. So let's go ahead and just set alpha to be 1, and then we'll store beta as an empty scalar, and then we'll actually comment that out, and then we run, and the same thing holds again. Since beta is empty, that error condition checks. Let's go ahead and test for non-double value now. So let's go ahead and store this as a single value. So this is single precision, and we run it and check it out. When we go here, both alpha and beta are scalars, which means we skip this value. But when we test this, one of those is not a double, which means we drop into this error condition, and that's exactly what we see. And the same is true if we change this. So if we change this to double and this to single, the same thing would be true. When I run this, my code catches the fact that one of them is not a double, and we produce the appropriate error message that we desired. We are slowly working through our list. Let's go ahead and comment that out since we've tested all those different values. And now we go over to the next one. So we've checked A, B, C. Let's go down to D. We need the input vector A to be a matrix, and it has to be stored in double precision. So if either of those things is not true, then we want to actually produce an error message. All right, let's go ahead and check for errors in the input A. We can go back up to the example that we're generating. In this case, we'll just copy and paste, and then we will uncomment this work. Notice that in this case, we actually are going to pass that alpha and beta work out all right. What we want to do is mess with our matrix A. Specifically, we want to pass a non-matrix or non-double matrix in. We'll play around with that in just a bit. Let's go over to our function file and actually code up an error condition that checks that A is non-empty and stored in double precision. One of the things that is interesting, that if I have a scalar A equal to the empty scalar, check this out, is scalar actually comes back as false. So an empty scalar does not satisfy the definition of scalar because the isScalar function is only true when the value has 1 by 1. But the same is not true for a matrix. Check this out. If I type A is zeros and perhaps it has 10 rows and 0 columns, that's an empty matrix. It has no information in it. And yet, when I type in is matrix A, that produces 1 for true. So in other words, the isScalar function behaves a little bit differently than the isMatrix function. If I'm going to check that A is a matrix, I have actually two different things to check. Number one, make sure it's not empty. Number two, make sure it's a matrix. With that, we'll use an if, else if, and then we'll have one more else if condition because we want to check that this is doubles, and then we'll end. The first thing that we're going to do is check is empty. So is the matrix A empty? If it is empty, let's remind the user that the input must be non-empty. The next thing we're going to check is A a matrix? Remember that is matrix A produces true when A is a matrix, but we want to produce an error message when that doesn't happen, so we'll hit it with a not condition. In that case, we'll go ahead and produce an error message that says the input array must be a matrix. The final thing we're going to do to sanitize the input data A is check that A indeed is stored in double precision, and we'll use the isA function. Remember, the isA function comes back as true when input A is indeed a double, but that's not when we want to produce an error message. We want that error to happen when this is not true. So specifically, again, we'll use the not operator, and we'll produce the error in that case that input A must be stored in double precision. Let's go back to our test driver. We'll actually take a look at all different versions of this. So the first thing that we'll do is we'll set up an empty matrix and then test to see what happens. Let's go ahead and do that and run. Check that the input must be non-empty. So we've now run into the exact condition that we expected. Let's go ahead and check matrices. In this case, is matrix means a two-dimensional array. We could actually try to come up with a three-dimensional array. Let me just show you what this looks like. We're not going to talk a lot about this in this particular class, but the point is that MATLAB allows for three-dimensional arrays. So an array of matrices, so to speak. And when we drop that in, notice that the is matrix function notices that this is not a two-dimensional array, it's a three-dimensional array. So this not condition evaluates as true, which means we drop into this error, and that's exactly what we see on screen. We've produced the warning that we wanted. The last situation happens when we store this in non-double, so we can actually typecast this as a single, which is single precision. And when I run this, we actually evaluate the third condition as true, which means we run the code in the body of that particular else if statement, and we produce that the input array must be stored as double. In other words, this else if statement does all the checks on the input data A to guarantee that it is as we desire. Let's go ahead and comment all of that out since we're not going to use it, and we'll move on to yet another input value check. From our specification list, the last error that we want to check is to make sure that the vectors x and y are both doubles and have proper dimensions. But that's actually not easy to do a priori. We actually have to do some processing work here. Recall that checking the dimensions of input vector x and y depends on both the value of the transpose character and also the size of the matrix A. So perhaps the first thing that we want to do is actually get the dimensions of the matrix A, and we're going to use our size function. We've done this in previous videos. We'll say that the number of rows of A is m, and the number of columns of A is n, and we're going to say those values are equal to the size of our matrix A. Moreover, the desired length for input vectors are dependent on whether or not the transpose input is n or t. So specifically, let's create a condition that allows us to check that. So we'll say this is going to be an else if, because there's two different values, and then we're going to end this. So we'll say for the first one, if the transpose is equal to capital N, then we're going to have the length of x as defined is going to be one thing, and the length of y is going to be another thing. Let's look at what that is. If the transpose is not going to be used, the number of rows of x should be equal to the number of columns of A, so that would be n, and then the number of rows of y should be equal to the number of rows of A, which should be m. On the other hand, if transpose is equal to t, in other words, we're going to be using the transpose in this calculation, the exact opposite is true, right? That the length of x should be m, and the length of y should be n. I did this out loud by thinking, let me check what I've already done to specify. Yep, that's right. So in the case that we don't use the transpose, x is an n by 1 and y is an m by 1. And the reverse is true in the case that we do use the transpose. All right, I'm feeling good. One of the subtle parts of this particular function is that we're allowing the user to set beta to be 0 and not have to specify the vector y, which means that we actually have to deal with the vector y depending on the value of beta. If beta is 0, then we define y. If beta is non-zero, we need to check that y has the proper dimensions. Let's go ahead and deal with both cases separately. The first thing that we'll do is let's go ahead and just check if beta is equal to 0, then we'll go ahead and define y to be zeros of the appropriate size. So remember, this is going to be the length of y comma 1. We're going to assume that y is always a column vector. So in the case that the user defines beta as 0, we simply set y to be 0. Let's check that that piece of code is working. Again, this is going to be non-zero scalar beta and vector y errors, so we're going to check for the proper handling. In this situation, let's use the previous calls that we've done. We spent a lot of time developing these. So here we're going to use a non-transpose. We have alpha as a double, we have beta as a double. Notice that beta is going to be zeros. And then what we want to do is actually produce y. So here, I'm going to go ahead and just print out y to remind myself. And then let's run. So here, input array must be stored as double. Oh yeah, of course, I'm reusing code that I did before. Let me just delete that, and we'll run one more time. Check it out. Y indeed was zeros of size 4 by 1, which is the exact dimension that I want from the example that I had. So that particular case is working well. If we have a 0 value of beta, the function simply defines y to be all zeros of the desired length that we need. The next question that we might ask ourselves is, well, what if we have a value of beta that is non-zero? In that case, we want to check if beta does not equal to 0. Well, if beta is non-zero, recall that the user has to define the value of y in the input, right? If the scalar beta, which we're trying to multiply by y, is non-zero, we need a vector to start with to do that multiplication. So the thing that we're going to say is, hey, user, if you define beta to be non-zero, then you have to give y as an argument. In other words, if n arg in does not equal to 6, and beta is non-zero, we should produce an error to remind the user what they're doing. In that case, we'll say that our error says, hey, when beta is non-zero, the vector y must be given an input. Let's go ahead and go over here. So check this out. We'll set beta equal to non-zero, but we won't pass a value y, and we expect in that situation that our error is produced, and that's exactly what we see here. All right, so now we've checked to see if beta is 0. If it's 0, we set y to be all zeros. If it's non-zero and the user doesn't pass in y, we tell the user, hey, get your act together. We have another condition, which is if beta is non-zero and the length of the input vector y is not correct, then we want to produce an error condition. So the specific thing that we're going to say here is if the size of the input is not equal to the appropriate size, so let's go ahead and think about this. Remember, we're thinking about the size of the vector as always being a column vector. Let's do some work here. So let's set y to be equal to zeros, and in this case it's going to be 5 by 1. And then we'll check size is a 5 by 1. Remember, in our example, the matrix we're using is a 4 by 3. So that means y would be a 4 by 1. So let's go ahead and check this. We see that this, oh, sorry, I messed up on that. Size of y is a row vector 5 and 1. And then what we're going to do is check, is the size of y equal to or not equal to the desired length? What we care about for the error message is if the size of y is not proper, then we're going to produce an error message. So what we're going to say is if the size of y is not equal to the desired size, which is 4 by 1. Okay, let's check this. We'll check this out. This is a row vector. This is a row vector. When we do not equal to, MATLAB checks the individual entries and produces a logical value in each coordinate. So here we see that the first entry is not the same, but the second entry is, which means that the first entry is true, it's not equal, but the second entry is equal. So we almost have the condition that we want. In other words, if the size of y is not equal to the length of y by 1, again, y is a column vector, then we're going to produce an error message. But remember that in else-if condition, we actually want this to be a logical scalar. This right here is not a logical scalar, it's a logical vector. And the size of that is a 1 by 2. What we really want to know is that these are identically equal. The only time that an entry would be not equal to logical 0, in other words, it would be false, is if one of these two wasn't equal. And specifically, in that case, if any of those values are not equal, then we say that the size of our desired vector y is not what we want it to be, and in that case, we want to produce an error message. Specifically, we're going to say that if you define a non-zero scalar beta, then you better put in a vector y that has the appropriate dimensions. If you don't, we're going to say the input vector y does not have the proper dimensions, which is exactly the error check we wanted to do. Let's go back to our driver and test that condition. In this case, we'll define the vector y to be, 1s, and we'll say that it's a 5 by 1. Of course, if we define that, we must also pass it into the function itself. And then when we run this thing, check it out, the dimensions of y are not as appropriate. Let's change to a row vector and see what happens there. Yep. Same problem. Okay, let's actually put the proper dimensions in and see that we don't get an error, which is exactly what we expected. So in this case, if my dimensions don't match what I need them to be, my error condition is running. All right, so we've checked all the different conditions. If beta is 0, we get something. If beta is non-zero, we're checking to make sure that the user actually passes in the y value and the size of the y value is appropriate. So if we get through all of these conditions, we're actually ready for the last piece, which is to set the value of y to be what we want it to be. So in this case, we're going to go down the individual rows of y and set each value equal to beta times the previous value. So let's see, the number of rows of y is going to be equal to the length of y, and then the ith entry of y is going to be beta times the previous ith entry of y, right? That's what we're saying there. So that would update my new values for y to be beta times the old values for y, which is exactly what we expect. Let's go ahead and just check that that's the case. And here we'll set this to be equal to 2. We'll set this to equal to 1. So we expect that the new value of 1 y is going to be 2 times 1, so all 2's. Let's run this thing, and that's exactly what we get. So, in other words, we've dealt with the input vector y as we desired in our specifications. All right, so we've checked that y has the proper dimensions. We're almost ready to check that x has the proper dimensions, but we have one other thing that we might want to be aware of. There's one value of alpha that is quite special. Specifically, if alpha is 0, we're done at this point. Because we've produced y is beta times y, we can actually write a quick if statement which says that if alpha is 0, just return the value of y that we've just calculated and get out of this function. So in that case, we're all done. It's not very interesting from the standpoint of matrix vector multiplication, since really this is a scalar vector multiplication, but it is valuable to avoid calculations with the matrix A if we don't need to do it. All right, that leads us to the last error check that we're going to make, which is on the dimensions of the vector x. Here we're going to use the same reason as we did above. Specifically, we're going to say that we want the size of x to be appropriate. So specifically, we want the size of x to be equal to the desired length of x for the number of rows, and then 1 for the number of columns. But remember, this would evaluate as true when that condition holds. We want to produce an error message that evaluates only when this condition evaluates as false. So we want that to be true. This is not a logical scalar. Remember that the size of x not equal to length 1, that's going to be a logical vector with 1 row and 2 columns. The error condition should be triggered when any of those logical scalars evaluates as 1. So we can use the any function, which we've seen from a previous video. So if any of these things are not equal, let's produce an error message that tells the user that the input vector does not have proper dimension. Let's go back into our driver, and in this case, we can just copy and paste. So I'll copy, comment. I probably should change this to a 5 because that's the condition that I was checking. And then we'll go down here. So y is good. Perhaps I actually run one more in x, which means that I'm not going to have the proper dimensions, and my claim is I should trigger this. Okay, let's go ahead and do that. So we trigger input vector x does not have the proper dimensions. That's exactly what I expected. So I'm kind of happy about that. So now we've checked that y is proper, x has proper dimensions. We have not yet checked that x is a double. So let's go ahead and do that. Else if, let's see. If x is a double, so let's check this, then we're happy. But we want to make sure that that happens. So if it's not a double, we'll produce an error message that reminds the user that x should be stored as a double. Let's go back over here. We'll delete that third entry since the values had to be proper. And then what we'll do is we'll typecast this as a single, and that's not a double. So we expect when we run this thing that the condition that we've just checked actually runs only when we have a non-double one-dimensional array, which is exactly what we see here, which means I believe we are now to a place 150 lines into our code that we've sanitized all the input. What are you noticing about the amount of work that it takes to make sure that the user is doing what you expect them to do? We're now ready to do our operation that we started with, and that operation is dependent on the value of transpose. At this point in our code, we already know that transpose is either capital N or T. So if the transpose input is equal to capital N, then we're going to do one thing. If that's not true, we know that it must be T because we've already error checked. So if this condition holds false, then let's drop into the else condition and we'll run it from there. Let's go ahead and remind ourselves that if transpose is capital N, we're going to form the vector y equals alpha times a times x plus y. And the reason this is in beta times y is because we've already overwritten y with beta times y. So hidden inside of this vector is the corresponding scalar vector multiplication that we wanted to begin with. Remember that we predetermined in the introduction to this video that we wanted to access our matrix by columns. So if we're going to multiply matrix A times vector X and we want to do it by columns, we're probably going to use our algorithm to do matrix column vector multiplication via linear combinations or axpy operations. Remember that algorithm is going to go over the columns of our matrix. So this is going to go from 1 to n. And then we're going to end this thing. And then what we're going to do is multiply the kth column of A by the kth entry of the vector X, and then by alpha. But remember, we can pass alpha in any direction. So let's go ahead and create a temporary variable, and we'll call it alpha times X And here's going to be the entry in the kth row. And then what we'll do is we'll say that the new value of y is going to be the old value of y plus our temporary variable times the kth column of A, and that's exactly what we wanted. So specifically, this is going to be an axpy operation. Scalar A times vector x plus vector y. The reason we call this BLOS level 2 is because it's one above BLOS level 1. This is not an entry by entry definition. This is a vector by vector definition. Now, we've done a lot of work to actually replace this with a for loop. So we could take this definition and actually go down to BLOS level 1. In this case, we'll go down the row. So for I goes from 1 to m. And then what we'll do is we'll take the ith entry of our desired vector y and store the previous ith entry plus the temporary variable that we've set up times the value in the ith entry of the kth column of A, which really achieves the exact same thing we just saw. It just does it entry by entry. If you need a reminder of how I did this algorithm, please see our previous videos. For those of you that are following along, go back and look at our program development process and map what we're doing to develop this production code into the different steps that we outlined in that process. Let's go back and ensure that the code that we wrote is working as we expect. So we'll go ahead and comment this, and we're now ready to verify output. In other words, we can actually collapse the section of error checking because we're done with that. And we can go into the output verification. Oh, I guess the one thing that I should do is actually grab the last bit of examples that I did, put them here, and then comment this out. So now we're there, and then I can actually collapse that section, which is really nice. We'll work with the first case where we don't want to add a scalar multiple of y, so we'll set beta to be 0, and then we won't actually pass y in explicitly, so we'll delete that part. And of course, we should delete the y as input here. So y out is going to be the output that we've generated with our function, but we might want to compare that to MATLAB's output. And in this case, MATLAB's output is going to be a times x. Let's go ahead and write this, and then what we'll do is we'll actually put these side by side. So on the left-hand side, let's put MATLAB's output, and on the right-hand side, let's put the output that we generate in our function, and then let's run, check it out. They're actually equal to each other, which is good news. That means that the algorithm that we're running seems to be doing what we want it to do. We could, of course, make this a lot more interesting by commenting these out and then just taking some random matrix. So you could check the function rand, what it does. Let's make it a little bit interesting. Let's do like a 40 by 20 matrix. And in this situation, if A is a 40 by 20 matrix, X would have to be a 20 by 1 vector. And then if we run, kind of hard to see. I mean, you can kind of see that they're equal, but this is not the best way to check output. So in this case, we're going to use a numerical analyst version of this, which is to look at the difference between the two of them. And we say that the two vectors are equal when the difference is close to 0. Oh my God. Those are exactly 0. This is pretty interesting. I was not expecting that. I was expecting them to be like 10 to the negative 6. I think what this means is that the way that we've written our function here is exactly the same computation that MATLAB does internally when we write this. That's pretty amazing. Another way to do this is actually take the norm and look at the difference. That provides a single scalar value, and if that scalar is close to 0, then we say that our desired output is very, very close to the native version of MATLAB. In either situation, we see that the work that we've done produces output that aligns with MATLAB's native functionality, which is exciting because it means our code is working. Let's generalize this and actually have a general alpha and a general beta. So we can reuse this code, which is exactly what we'll do. Here we'll drop it there and we'll uncomment, which is really nice. And beta, we're going to assume, let's go like -3 or 3. It doesn't really matter. Alpha we'll do 2. And then, of course, if we said that beta is non-zero, that immediately implies that we've got to store y explicitly. In this case, I'll define y to be kind of a transform 1, -1, 1, -1, and then I'll pass y in. And of course, in this case, we're going to use MATLAB's functionality inside to check that our work matches their work. So let's go ahead and run this. Check that out. It happened so fast you didn't even see it, huh? the output that we generate, y out, is identical to the output that MATLAB generates, y mat, which means that this part of our function is working properly. That's really exciting. Okay, so we've now checked the first condition where we have the capital N value. Let's go on to the second condition. If it's the case that transpose is not equal to capital N, that must mean that it's equal to capital T because of our error checks above, in which case we want to form a vector that is alpha times A transpose times X plus beta times y. Remember, beta times y is hidden above in our code. Remember also that we want to process the columns of A. In order to process the columns of A when multiplying by the transpose, the columns of A are the rows of the transpose. In other words, we could do this multiplication row by row, but to do this multiplication row by row, that means we're going to use the dot product version of matrix vector multiplication. For that dot product version, remember, we're going to go over the column, so this is going to go from 1 to n. And then what we're going to do is overwrite the kth value in y with the previous kth value plus the dot product between the kth column of A, which is what we wanted to access, and the vector x, right? The reason that we're doing the kth column is that we're trying to multiply the rows of A transpose, but the rows of A transpose are the columns of A, and this should actually produce what we expected to do. But notice we call this BLOS level 2 because this is not down at the entry by entry level. This is processing data at the vector level. We've seen in previous videos how to exchange this particular line of code with an entry by entry version using for loops, and that's exactly what we'll do here. So specifically, if I want to actually run through the dot product via for loops, the first thing that I need is I need a temporary value for the scalar that I'm trying to produce, and then I'm going to run through each individual entry in the kth column. The kth column of A has m rows, so in this case we're going to run through the rows of A. And then we're going to say that what we wanted to produce is this. So the new value of temp is going to be the old value of temp, starting with 0, plus, well, let's think about this. I'm going to take the ith entry of the kth row and multiply that by the ith entry of x. And I go all the way down. So by the time I finish this inner loop, temp is going to store the dot product that I want. So specifically, we're going to go ahead and overwrite this with temp. But remember, that would only give me A transpose times X. I still need alpha. So if I multiply this by alpha, that should give me the exact value that I want. And then I add that to the previous value of Y and use that location to store the output. Okay, so I think this is working properly. The insights, if you're curious about how I got these insights, go check out our previous videos on matrix vector multiplication. Of course, when I'm done with this, I'm going to store the value sitting in Y as my output, and I'm going to return control to the script file that is driving this. Okay, let's go ahead and comment this out, and we've tested the matrix column vector multiplication both in specific and generalized form. Let's do the same thing for the matrix row vector multiplication. And in this case, that means I'm going to be using the transpose to calculate. I'll start with the easiest case first, where alpha is 1 and beta is 0. And then again, we're going to use the previous example that we've done with MATLAB, which is a row vector times a matrix. In this case, because we're using the transpose, the output is going to be stored as a column vector. But to get the desired output, we would just take the transpose of it. So let's go ahead and run this and see that the output that we produce is equivalent to MATLAB's output. So when we run it, let's go ahead and check. So we'll look at the norm between the difference of y mat, which is MATLAB's native output, and y out, which is the output we generated in this function. Check that out. The norm is 0, which says MATLAB produces the exact same thing as we do. Of course, we could change this to random data. How excited are you feeling? Do you want to see if we could break MATLAB? So let's do 1,000 by 500. And then this means that this is going to be something like that. So if this is 1,000 by 500 and we're using the transpose, the number of rows of X must match the number of rows of A. So this is going to be 1,000 by 1. Let's go ahead and run this. Oh my God. So this isn't exact. So check this out. This is actually not that great, but for the size of our data, we'll say that it's acceptable. The point is that this is pretty close to 0 though, which means that the algorithm that we're using produces data that is very similar to the algorithm that MATLAB uses. It's not identical to, though, right? Let's see what happens if we change the dimensions a little bit. So let's go down and just see if that affects this at all and run. Yeah, this means that the way that MATLAB is calculating this is probably different. The sequence of operations they use is different than the sequence of operations that we use. It's still close to 0, but it's not exactly 0. Okay, so we've done this situation where we're actually checking our algorithm for a case that we know, and we look at the difference. The last thing we're going to do is verify that when we have a non-zero value for beta and a non-1 value for alpha, that our algorithm still works as expected. So we'll just go ahead and copy and paste. In this case, we'll set beta to be equal to, I don't know, -2, and we'll set alpha to be equal to 5, I suppose. And of course, as beta is non-zero, I do need to actually define y, and then I need to pass y into my function, which is what I'll do here. And let's change this. This is going to be alpha times A transpose times X plus beta times y. And then we need to compare MATLAB's output with our output. And indeed, in the integer matrix coefficients that I use for our example, the algorithm we've written matches identically what MATLAB produces, which means we're feeling pretty good about this algorithm. Okay, we are now done implementing our general matrix vector multiplication on double valued outputs. Check this out. Out of the 176 lines of code, really only like, I don't know, what is this? 5 of those lines do it. But we've coded in a bunch of functionality and a lot of error checking to make sure that we sanitize our data and run through the memory of our matrix in the exact way that would optimize our code. Welcome to a major theme in linear algebra, which is it takes a lot of work to get a good production code. Once we've done this, however, anytime we want to do matrix vector multiplication, we have a function to accomplish that, which is quite powerful. I'll say this again and again and again. This is exactly what Cleve Moeller did in the 1980s as a precursor to MATLAB. And indeed, if we were to look at the files that create MATLAB as a programming language, somewhere in the depths of their libraries would be a function that looks very similar to this, maybe written in C or Java or Python. I'm not sure what the most recent version of MATLAB is written in. The fact of the matter, though, is we are doing the exact same type of coding that provides the core of so much of MATLAB's capacity. That leads us to the community challenge for this video. What we've done in this particular function is to code algorithms that access A in terms of its columns. The challenge I have for you is to write a separate function that does so using the rows of A. So imagine that you were working in a programming language that actually stored A based on its rows, and you wanted to optimize the way that your code ran by running through the rows of A. What would you need to do to change this function? Yet another community challenge is to share in the comment section below your reaction to this type of coding. What comes up for you? What do you think of it? What are some things that catch your attention? What are some struggles you're having? Thank you so much for your attention, y'all. I appreciate it. We're building our libraries, and I'm so proud of your grit and determination. You are building your skills day by day. I'll see you in the next video.